45 minutes, right? So, as I said, we're going to now talk about a concrete example, very classical numerical geometry question. And I'm going to try to use graphical geometry to revisit the same question and hopefully say something interesting about it. This slide, as I said, everything is joint work in progress with Anna, well, Johan Len, Anna Martek, who by the way says hi, I just visited her, and sends best regards. And you hopefully be at the art sometime soon. I forgot to say. So I brought a handout because I didn't bring it. No. Gladly, kindly, Karin and Martin did some copies, so this will be something for you to follow along. And there's more copies if you want it out. Okay, so let's talk about the classical question. So, goes as follows. So I'm gonna take sextic. So a sextic curve given as the intersection of a conic and a cubic. In P3, let's say over the complex numbers. Is a smooth quadrant. So it's a variety of Q, where Q is homogeneous degree 2 polynomial with 4 variables. You can think of it as a preferred conic, maybe the one that is the image of the Saturn embedding. So G0, C1 minus C2 times C3. And C is a smooth cubic surface. So again, this is going to be given by a homogeneous degree 3 polynomial. With the variables. So if you think about this, what's the expected degree of this thing? Well, the Zoom tells us that I'm going to have something.
K? Q. K? Q.
Oh, Q, sorry.
K, rather.
Sorry. K, yeah. Q and K. Thank you. So I'm going to have something of degree 2 and something of degree 3. So I would expect that C is a degree 6 curve, a smooth curve. So that's our classical object. And of course, we know that, degree 6 will say, well, the number of intersection points between C and H, the general hyperplane. So we should get 6 different points. And then if pairs of points start coming together, we're going to start having higher multiplicity points. And so parency corresponds to let's say parency between E and let's say special H corresponds to pairs of contact points coming together. Points. So the question is, well, can I make a choice of a special point so that these 6 points become 3 points of multiplicity 2 each, or maybe even further agreements. Okay, so by definition, for tangent and tritangent plane, H to C. It's a plane that meets C at points of even multiplicity. The combinations could be 3 points of multiplicity 2 each, 1 point of multiplicity 4 and 1 of multiplicity 2, or maybe 6 comes together, and then I get 1 point of multiplicity. Okay, but I don't want something like 3 plus 3. Okay, so of course the question is, how many can we get? We have, and well, you can first do a naive count in terms of computing, given an ideal that describes exactly this and finding the solution to this, right? So, so the ideal computation you can do will be, well, I have, let's say my H is going to be A0, D0 plus A1, D1, A2, D2, plus A3, D3. So I'm going to associate this with a point corresponding to the coefficients. So this will be a point in the dual, or P3 dual. So again, we're going to identify with P3 by this concrete map. And so I'm going to look at the possible couples of the scalar such that we can find 3 points, P1, P2, P3, and P3. Just trying to describe the most general situation where the 3 points are different. And so what do I need? Well, if I want to solve this question, remember we have these polynomials. So on the one hand, I have my degree 2 polynomial. So this P better vanish on my quadrant. It also better vanish on the cubic. And it also, maybe I should say H is the variety of this, and we call this polynomial H. So my H is going to be 0, so that says just the points lie where they should. And then how do I record the tendency condition? Well, you can just look at the Jacobian of Q, F, and H. Q, F, and H. Evaluated as PI, and this should be non-invertible, and that should be 4. So all of these things should vanish. So I get, for each point, I get 4 equations. So I have 4 times 3 equations. In, let's say, 12 variables if you, after the homogenization. Yeah. So if my polynomials Q and F were general, so my coefficients were general, then I should expect this to have a finite count. So I have 12 variables, same number of equations, I should expect finite units. So for Q, F, general, you expect a finite count. And you can do this for some examples, and then you can see that in fact we get generally we get the same number, and that's going to be 120 times 3 factorial, which is 720. And the 3 factorial comes because I made a choice of labeling my 3 points, but if I flip them around, I should get the same solution. So every honest tritangent will come from 6 of the solutions. Okay. So the magic number is 120. So that's the number we expect. So of course, this is not the way that this classical question was answered. So back in the day, so a theorem of Clebsch from 1863 says that this number is actually correct. C has exactly 120 right tangents. And so they correspond to odd theta characteristics on the curve, right? So you can count the number of odd theta characteristics, that gives you 120, and it matches this. Okay, so natural questions that you can ask. Well, I know the number, but if there's a Q and an F that come through this door and says, well, can you actually compute these tritangents? Well, there should be something that we can do, right? The first question is, can we actually compute them? And the second question would be, well, we work with the complex numbers, that's fine, but there's other fields that we can consider. Right? So what happens, or how many do we have over other fields? So, example, well, let's say over the reals, we can have two sorts of questions. Well, so how many tritangents are actually defined over the reals? So meaning the A's, the corresponding coefficients are real. Will be one question. So these are real tritangents. Real not in the sense of true, but real that defined over the real. And the second question are the tangency points real or not? So my equation is defined over the reals. I have the hope of finding real solutions. But then we can have two situations. We can have 3 real points, or 1 real and 1 complex conjugate pair. Right? And so the situation here where the line and the tangency points are all real, this is a case of what we call a totally real tritangent. And so the question is not really so clear. How do we, what numbers do we expect, and can we actually find examples for these numbers? And so in the last, I think, decade, there's a lot of people that got interested in this question, and it stemmed from an error in an old computation. So there was an example, I think, by M that said, we wanted to find a real Sextic curve that had exactly 120 totally real, so where you can actually see the tangency points and the right tangent planes. And there was a mistake in the calculation, and the example didn't have exactly 120, but it had only 108. So then, the question is, well, can we actually find one with 120? And well, can we actually find different combinations of how many if we know the number of real right tangents, how many are totally real, how many not? Can we change examples and get all these possible numbers? Right? So there's a lot of people interested in this question. And so the first question is, well, what numbers do we expect? What are the possible combinations? So there's a theorem by Goethe and Harris from 1981. Same result appears in a paper by Krasnov from 1998 that says the number of real depends on the topology of the real locus. Depends on the topology of the real locus. So this is the real locus of C. So let's say my curve was defined with real coefficients, so my Q and my F were real. I have complex solutions. I know there's 120 of these complex Tritangents. And then I'm just looking at the real picture and trying to see how many of these are actually real. And so the topology here, I mean the number of connected components of the real part. And the question is whether if I look at the actual complex curve, I remove the real locus, is this connected or not connected? Okay, so if the real co-locus divides the complex locus or doesn't divide, I will get different answers. And so the options are opposed for the real number. The number of real Tritangents, they're always going to be multiples of 8. So I'm going to get 0, 8, 16, 24, 37, 64, and finally 120. All of them are, so there are examples of this. And then this corresponds to the number of connected components being either 0, 1, 2, 3, 4, or correct? Yeah, 5. Good. And then depending on if it's a dividing type or not, I will say if the real locus doesn't divide, we get the first 3. I get this number if it divides. Then for 3 connect components to undivided type, the number jumps. And finally, this will be the maximal number of connected components is always of dividing type, and I'm getting 100. So there's a numerology. So the question for real Tritangents is settled. Of course, now the question, as I said, is how many are totally real? How many of them have all the Tritangent points, the tangency points real among this? The equation could be real, but as I said, you could have one set of complex conjugate pairs of tangency points. So those are not the ones that we want.
Angie,
yes.
Do I remember correctly? A minute ago, you said Klebsch examples I had 108 and 108.
No, not Klebsch. M-E-M-R-E.
Okay, but 108 still doesn't figure in that list you just wrote.
Sorry, 108 totally real.
Oh.
Yeah. So the point was that they computed totally real, and the question now, of course, when you get this one, you know the 120 complex, you want to know how many of them are not just real, but totally real, because I can just draw it. And so in that paper, there's a calculation that said, yeah, this example is 120, and then Corey Harris and Yoav Len revisited this question in 2016, and they said, oh no, that number is not correct. The example was kind of 108 totally real. So then the search started back again. So this question is still open. And so now, again, the solve the question. So the totally real number. What happened was, so Maya Boomer.
Can you tell us what totally real means?
So all tangency points are also real.
Ah, okay.
Yeah.
Oh, right. Thanks. Sorry, didn't see that.
No, that's fine. I'm bound to forget stuff, so please ask me questions. So in 2018, Maria Boomer actually gave bounds for how many, so at least how many are totally real, and at most how many are totally real for each one of these different numbers. And so there's a range of totally reals. So for the first one, of course, there is no real there can't be any totally real, so first one is easy. For 8, the range is, well, maybe none of them are totally real, or at most 8 are totally real. And you can keep going. First examples are not very interesting. You can go between 0 and all of them are totally real. And then for these examples, it starts getting more interesting. You get, if you have 32 reals, then at least 8 of them are totally real, and at most 32. Then you can have for 64, at least half are totally real. And you can go all the way to 64. And then you can have at least 80 and at most 120 totally real. So these are bounds for the number of totally real. So these are proposed bounds for this count. And of course, the question is, well, how many of these bounds are actually typed? Okay? The question is.
So proposed bounds means those bounds hold, or they are just suggestions? Yeah, as of now.
Proposed bounds for this I say proof bounds.
Okay.
Very, very more precise. Proof bounds for the number of totally real, and these are the numbers. And the way he did it was, as I said earlier, Clerch did this calculation via theta characteristics, and this calculation is done via real theta characteristics. Yes?
Is this saying there should be a different way to count so it's not quite as case-based? Or like...
I don't know what you mean.
I mean, there's a lot of different cases, you know, from 0 to 120, all of these bounds, but is there like...
Yeah, there is a formula. So I'm just trying to illustrate the bounds, but yeah. There is a precise formula for the number of totally real odd real theta characteristics. Sorry, number of odd real theta characteristics, and then you get these. Right, that's the calculation for the number of real tritangents, and then there's another calculation you can do. There are four. And so the question is, are these bounds typed? And so all that was, the answer is yes, in almost all cases. There's only one case open. I'm telling you this not because we can actually solve it, but because maybe some of you would be interested in this question. So precisely is that, so how is he Ukraini, circles, sorry. And at the same time, gave proved examples provided maybe for all cases except for the case of 120 real tritangents. So the examples are, so we have examples with 84 totally real. So that's the best lower bound examples I can find, and 120 totally real. So the only missing examples are, can I find one with 80? Maybe I can find one, if not, I can find one with 81 perhaps, 82, or 83. But then there's examples for 84. So that's sort of the state of the art right now. Okay, so
They found everything true, or did they
they definitely found extreme. So the difficulty in this paper is that it's done via numerical calculations. So they have an example where they know, they start from something where they can compute, and then they do some homotopy and find examples technically that have this number, and they have a way of certifying that the actual solutions, you will get complex conjugate pairs or, so, but there's no actually equation. So I believe these guys, but I'm saying if you want to actually go and find it, it might be difficult. Okay, they have the paper has all this code online, so you can actually go and use it if you want to try to play with examples or. Questions? Okay, so maybe this is okay. So again, as I said, I'm not going to be able to answer that question, but I would like to sort of revisit this 120 count and the number of real tritangents and try to do this properly. So I'm going to start by doing some reduction in dimension because I don't like to draw in free space. So first we can reduce dimension. As I said earlier, we have our T was the conic intersect the cubic. And we're going to take our favorite conic to be V0, V1 minus V2, V3. And this is isomorphic to T1 cross T1 via the second day. If I do this, then I'm bound to computing bulldogs of these equations. And so in T, sorry, the P1 cross P1, T is the vanishing locus of a degree 3-3 equation, let's say degree 3-3 polynomial. And my hyperplane is going to be the vanishing locus of a 1-1 degree in variable x, degree 1 and degree 1 in y. So this is a P1 plus. So now in terms of my Newton polytopes, which is the thing that we needed for our tropical business, the Newton polytope for the little h, this guy, let me change and call L, because that's the notation we have on the paper. And this guy, let me keep it simple and use the same letter. So this guy, again, it's a 1-1 curve, so sorry, we're going to have exactly degree at most 1 in x and at most 1 in y. So that's going to be the polytope for h. And for the for my cubic, I'm going to have a polytope, so the square of side length 3. So you observe here that you have 4 lattice points, which is sort of in agreement with the fact that the classical curve has genus 4. And so if I wanted to tropicalize this, well, we know that we need to build dual subdivisions to these pictures over here. And now, the tangency point is easy to determine because I have just 2 equations. And so the tangency points now, P is a tangency point. If we have F vanishes at P, L vanishes at P, and then I have the determinant of the Jacobian matrix also vanishes at P, and this is known as the Wronskian. So now I have fewer equations, and that should make my life easier. So now this is the setup, and I would like to try to study this on the tropical world. So we saw in the examples before what was a tropical tangent point, and I would like to now try to see when the tropicalization of this L is tritangent to the tropicalization of that 3-3. Okay, so our tropical approach. Will be as follows. So we're going to fix once and for all our sextic, or so our 3-3 curve. I'm going to have a gamma, which is smooth. So let's say the tropicalization of C. Inside, let's just work on the alpha patch. So we're going to work with in R2. So this again is going to be a dual to a unimodular triangulation of the square of side length. So in the handout, we have a lot of examples of this. So there's a lot of examples. So that's my input. And to make my life easier, I'm going to assume the edges are general. So the edge lengths of gamma are general, because some of our relies on this, but it's not really too bad. So if you consider all possible edge lengths or some things that should be different to prevent some weird alignments from happening, like I should erase this. So that's our input. And now I would like to find 1-1 curves that are tropically tritangent to this one. So our 1-1 curve, again, it should be a subdivision, so dual to a subdivision of this square of side length 1. And so the tropical 1-1 curves are going to come in 3 types. They're going to be dual to this positive subdivision. So one option is to have something like this. The other one will be a subdivision goes the other way around. Or maybe I can have a situation where there's no further subdivision. So these kind of pictures should appear. They're not smooth, but it's a fact of life, they're there. So we'll have to deal with them. They're not necessarily smooth. So the last one is not a smooth one. And so, as I said, heuristically, if I have a tritangent triple, so L gives me the equation for the tritangent and the 3 of the tangency points for tritangent triple with C, which again was V of F. Then, well, tropicalizing the line and tropicalizing the points by just looking at their negative relation should be a tritangent triple. Okay, we haven't defined it yet, but it should be a tropical tritangent. Should be a tropical tritangent. Let's say should be tropical, a tropical tritangent triple to my input firm. And so of course, we can sort of use examples if you want to try to guess what the right definition should be. That's one way of doing it. And what we did was sort of build our understanding of the tangent situation to try to give a right definition. So this is going to be my gamma is my letter for my tropical 1-1 curves. So this is going to be tritangent to gamma if I compute the set intersection as we did with the conics and the line. And we have 3 situations. In the conic case, we had 2 possibilities. One, we had only one in the conic case, but here 3 things could happen. I could have one connected component of total intersection multiplicity 6, right? The number should give me the degree, so 3 plus 3 is 6. I could have 2 connected components of one of multiplicity 4 and the other one will multiply by 2. And the third situation will be 3 connected components of multiplicity 2 each. Okay. So that's my heuristic definition. And so, of course, the goal is to try to give a combinatorial characterization of what do these things look like, what does a local tangency look like, and well, once we determine what these things are, which of them actually come from tritangents, and when we actually compute the elliptic multiplicity. So the goal is to characterize local tangencies. And we will have 3, like we have 3 multiplicity 2 components, and you'll have 2, one of multiplicity 2 and one of multiplicity 4, or I can have 1 connected component of multiplicity 6. Second one will be actually find all tritangencies. And the third question, as I said, is determine lifting multiplicity. Which one of them actually come from classical ones and from common. So the first theorem is the one you have on your pictures you have on the handout. So all these different combinatorial types appear on the handout. There are exactly 40 of them. A little bit more complicated because my one curve is more complicated than the classical situation with that line. So I have more possibilities. Yeah. Theorem 1, same set of authors. So there are 40 combinatorial types of local tangencies. Local tangencies, sorry. And then, as we had with the conics, we can move a given tritangent, maybe while preserving the tritangency condition or not. Sometimes we're stuck and we can move it, but sometimes we can. So we can define equivalence classes of tritangents under, let's say, translation plus information of the length of the bounded edge. So in the conic, I had no freedom to move the vertex. Here I have 2 vertices, so I can sort of displace both of them. That means either stretching or shrinking the edge of the bounded, the bounded edge of the lambda curve. And so the question is, well, how many can we have if we maybe identify these things? So one thing is that we can move things and while preserving, finish my sentence, equivalent values of tritangents on the translation and information that preserve tritangent condition. And the reality is that often we have infinitely many tritangents, which is that we have superabundance. But we can sort of try to understand if this equivalence values are still infinite, and in fact are not. So a theorem of Harris and Len was that there exist exactly 15 equivalent classes of tritangents. Of x gamma. So the number goes from infinite to 15. It's still not 120, but they also show that each tritangent class has the tropicalization of 8 of these tritangents, of 8 classical tritangents. So that is good because 15 times 8 is 120. So all these classes contain multiplicity. There are correct number. And so another question is, well, can we actually see on each tritangent class which one's left and with what multiplicity? And that's our result. So so the theorem 3 is that we have lifting multiplicities each type. So local lifting multiplicities that can be combined. And each one that lifts with either multiplicity 1, 2, 4, or 8. So for example, if you have a tritangent that doesn't move, then that guy is the tropicalization of 8 classical tritangents. But we can say, well, how many of them can we combine? So how can we make 8 out of adding numbers like this? Well, in principle, there's 10 options, but there's only 6 possible lifting partitions. So combinations that give me 8. So we can have 8 ones that lift with multiplicity 1 each. We can have 4 that lift with multiplicity 2. We can have 2 of them that lift with multiplicity 4 each, or I can have one example, so it's 1 point that has to lift with multiplicity 8. Or I can have 2 more examples. I can have 4 that lift with multiplicity 1 and 2 that lift with multiplicity 2. And finally, I can have 1 that lifts with multiplicity 4 and 2 that lift with multiplicity 2. So out of the 10 possible, only 6 occur. And in the handout there are examples of, you can see examples where you can see these different times. And the last thing I'll say, this will end, is that the question of the reals, we can't really answer much, but we can say something. So each class, let's say if we work, maybe we'll be more precise, if we work over a real closed field, for example, Cueto series, but now with real coefficients, not complex, then each class, each tritangent class has 0 or 8 lifts. 0 or 8 lifts to tritangents over this value field. And the sad thing is that they're all totally real. Moreover, they are always totally real. So, as I said at the beginning, this method is really not helpful if you want to improve these finding examples that don't achieve this upper bound. But when we started, there were no examples of achieving 120. So when we started, so this is great, we can do this. But then, of course, we were too slow and somebody did it, but the things are still out there. So there's something you can say, but the tropical method, at least if you work on the planar embedding, you're not gonna be able to find interesting examples that have different numbers of real and both objects, whatever you want. Okay, so that's all that.